Hello, my name is Jason. Welcome to my heat transfer video assignment. In this video, I'm going to be going over a transient heat conduction problem. So let's get started. So we'll start with the problem statement. I'll just read it once and then I'll read it again, picking out some key information. So in a metal processing plant, droplets of molten metal are formed initially at a temperature of 1400 Kelvin. The droplets are cooled by being placed in a medium of 300 Kelvin. The heat transfer coefficients are 6000. Radiation losses may be neglected. The properties of molten metal are the following: thermal conductivity of 60, heat capacity of zero point 0.4, and a density of 9,000. So kind of going over this again, we can assume a diameter of 2 centimeters, initial temperature is 1400 Kelvin, surrounding temperature is 300 Kelvin, convection coefficient is 6000, conduction coefficient is 60, heat capacity is zero point 0.4, and density is 9,000. Great. So going over the problem statement, in part A, we're going to be assuming a lumped system model is valid. So determine the temperature of the droplet after 4 seconds, calculate the total energy loss of the droplet, evaluate the validity of the uniform temperature assumption, and then discuss your assumptions and how they're affecting your solution. So tackling this first part, they give us some additional information that time is 4 seconds, and we'll also be assuming a lumped system. So now we'll just go over some assumptions. So the question said to assume a lumped system. Usually we would do a quick check to see if this is allowed, but I'm going to skip that for now. The question also said we can neglect radiation. I'm going to assume there's no heat generation, constant thermal properties of the material and the surroundings. I'm going to assume this is a one-dimensional equation such that heat transfer is only traveling in the radial direction. It's not traveling in any of the theta or psi directions. We're going to assume a uniform spherical shape. The question said it was a droplet, but we'll just assume it's a sphere. So the schematic for this is just a regular sphere with heat traveling from the center to the surface, and then from the surface to the environment. So the governing equations for this, so for the lumped system situation, normally, like I said, we would check for the Biot number and check if this condition is valid, but we're going to be skipping that. So here's the equation for the lumped system. We know T infinity, we know the initial temperature, we are looking for the time after 4 seconds. So we know the time. We don't know this B value, but we can calculate it pretty easily. We know H, we know density, we know CP. We can calculate the surface area of the sphere. We can also calculate the volume of the sphere. So we're good for this. So at this point, it's just a plug and play problem. Just a note, I did convert my units to SI units, so I have the diameter in meters and I have the CP value in joules per Kelvin. And yeah, we get a temperature of 449. So moving on to the next step, calculate the total energy lost by the droplet during this time. So to calculate the total energy loss, we can use this equation here, mc delta T equals Q. We can figure out M by multiplying the density times the volume. We know Cp, and we can calculate delta T. We just got it from the previous step. So plugging in the numbers, we get this. Like I said, density times volume gives us our mass, and we end up with 14.3 kilojoules. So moving on, evaluate the validity of the uniform temperature assumption provided in your reasoning. So in order to calculate the validity of the lumped system analysis, we first have to calculate the Biot number. This is a simple calculation that compares the convection coefficient with the conduction coefficient, then multiplies them by the characteristic length. So if this number is less than 0.1, we're good to assume a lumped assumption. Doing this calculation, we can see that the Biot number is greater than 0.1, and so a lumped analysis is not valid here. Just taking a deeper look at this equation, I want to make some comments. The ratio between the convection and the conduction is rather high. This would imply that heat transfer at the surface is happening much faster than heat transfer within the body. This would make it obvious that a lumped analysis wouldn't be valid here. However, taking a look at the ratio between the volume and the surface area, this is much lower, and so we would imply that a lumped analysis is valid here. So initially, it's not so obvious whether you can make the lumped analysis assumption or not. You would have to do this kind of calculation beforehand. So moving on, discuss how your assumption, other than the lumped system assumption, is affecting the solution. What would change if any of your assumptions were not valid? So looking at our assumptions again, if we were to neglect radiation, the process would be the same. We would still use the same equation, but we would have to recalculate B because B depends on H. And if radiation was involved, I believe H would go up and the overall temperature, the overall heat rate leaving the system would increase, and so after the same amount of time, 4 seconds, I believe the temperature would be a lot cooler, closer to the environmental temperature. For any of our assumptions, I believe we would have to use the big original heat transfer equation in spherical coordinates. If we couldn't assume no heat generation, then I believe we would have to include the term. If we couldn't assume constant thermal properties, then we would have to integrate each one accordingly as temperature changes. If we can't assume one-dimensional, then I believe we'd have to use the remaining dimensions in this coordinate system, not just the radial one, but also the theta and the psi directions. And if we couldn't assume a uniform spherical shape, then I believe we would have to integrate each term to their respective limits of integration. And this whole process just becomes a lot more complicated. So moving on to part B, evaluate the validity of the uniform temperature assumption. So we kind of did this earlier in part A. We just checked the Viet number and we saw that it was greater than 0.1. And so, it's not necessarily a valid assumption in this case. So moving on, if your answer is invalid, determine the temperature at the surface of the sphere and the total energy lost by the droplet during this time. Do not use the Heisler charts. That's great because I don't even know what that is. So I'm just going to focus on this first part, determining the temperature at the surface. So same assumptions as before, but we're not going to use the lump to system analysis. So the governing equation this time is this. This is an infinite series sum, which is quite a pain. So we can calculate the Fourier number, and if this number is greater than 0.2, then we can reduce this equation down to the approximate solution. This is just taking the first summation in that infinite summation series. So here it is. Looking at this equation a bit more in detail, there's some values we don't know. We don't know a1 and lambda 1, but we can easily find those values from looking at table 4-2. Here in this spherical column, they give us lambda 1 and a1. So now we would know all the values needed to solve for this. So I just want to go over the workflow for doing this kind of question. So we're given the exact solution, but we can do a quick check to see if the Fourier number is greater than 0.2. If it is, then we can use the approximate solution. To use the approximate solution, we need to find values from table 4-2, and then from there we can plug everything into the approximate equation and solve for temperature at any given radius or any given time. So first thing we're going to do is to calculate our Fourier number and check to see if it's greater than 0.2. The equation for calculating it is alpha t over L squared. To calculate alpha, we can use this equation, k over rho c. Plugging the numbers back in, we get a tau value of 0.66. And great, this is larger than 0.2, so we're good to proceed. So now we know our tau value, and we just have to calculate for a1 and lambda 1. We'll get this from the following table. Moving over to table 4-2, it's pretty easy. First we have to calculate the new Vyan number, which is just hr over k. We have all these values, so Vyan number is 1. Looking at the table, we see when Vyan number is 1 for a spherical, we get the corresponding lambda and a1 values. So now we're ready to plug everything into this equation. Just a note, there is an r over r naught term, and since we're calculating the temperature at the surface of the sphere, this term just goes straight to 1, so I'm not going to include it in the following calculation. Here we get our results, and we can see that the temperature at the surface is actually 304 Kelvin. So moving on to the second part of this question, it says to calculate the total energy lost by the droplet. So moving on to calculate the Q for the system, here's the equation we can use. It depends on this new term called theta of 0, and this is just saying, the temperature at the center of the sphere. So we already know the values to calculate this. We know a1, lambda 1, and tau. Plugging those in real quickly, we get this. Next we need to find Q max, and to find that we can use the same equation, mc delta t. Just note that delta t here is, T infinity minus T initial. Plugging those numbers in, we get this. We get a value of 16.5 kilojoules. So now using our Q max value and our theta 0 values, we can sub it into the equation and solve for Q. We get a number of 21.4 kilojoules. This is kind of counterintuitive because this Q value is larger than Q max that we previously calculated. The reason for this could be because sine of a small number is 0, and so this upper expression is the dominating term, which is a negative term, and so this whole expression becomes negative, and so 1 minus a negative number will be a number greater than 1, and so Q max times a number greater than 1 will result in an even greater number. So kind of counterintuitive, but that's what we got. So at this point, we are done. We've answered all the questions assigned. So before we end off, I'll just do a little bit of a discussion. First thing we did was we calculated the Viet number, and because it was greater than zero point 0.1, we concluded that doing a lumped analysis here would not be effective. But we went ahead anyway, and we did a lumped assumption analysis and a spatial analysis. We calculated the surface temperature after 4 seconds 2 different ways, and as you can see, we got two different numbers, and so this kind of reinforces what we learned that if the Viet number is not small, then doing a lumped assumption is not valid. So yeah, that was good. So thank you for your time and attention. I hope you enjoyed my video.